Well, hello again. This is the first lesson from Chapter 5 in which the focus shifts from understanding trigonometric functions as an angle and standard position to taking that into understanding them as functions that can be graphed and transformed and modeling and can be used to model scenarios as well. Although, again, it all builds upon the key ideas of Chapter 4, especially special angles. And what do you know? I start with special angles here. And so the first thing I want to do is develop a good idea for how sine and cosine behave. And most of this chapter will focus on sine and cosine. Tangent is a relatively small part of this chapter, so expect to see sine and cosine predominantly. So for how does a sine function behave? Let's create a table and pick values of x. I'm picking all multiples of 45 degrees. Every single one of these values is a multiple of 45 degrees. 0, 45, 90, and so on. And so the sine of 0 is 0. The sine of 45 degrees is 1 over root 2. However, I want to graph this in a moment, so it's probably a little more useful for me to decimalize 1 over root 2, which comes to about root 7. Sorry, not root 7, about 0.7. The sine of pi over 2 is exactly 1. In the second quadrant, sine starts to go back down. The sine of 3 pi over 4 is the exact same thing as the sine of pi over 4. So it's about 0.7. It's exactly 1 over root 2, but for graphing on this grid, 0.7 is more useful. The sine of pi is the exact same as the sine of 0, which is 0. Now we're in the third quadrant, which sine is negative. The sine of 5 pi over 4 is about negative 0.7. 3 pi over 2 is between the third and fourth quadrants. And at that point, sine is exactly negative 1. And then 7 pi over 4 is in the fourth quadrant. Sine is negative again, so it's negative 0.7. And 2 pi is coterminal with 0, so sine is 0. So everything I did there quite quickly, I'll admit, goes back to our special angles from Chapter 4. So let's graph these now. So the sine of 0 is 0. Now notice my scale here. My x is going up actually in quarters, I believe. Yep. My y-axis, the major grid lines are at multiples of pi over 2. And so pi over 4 is going to be actually right here. That's what halfway between 0 and pi over 2. And 0.7 will be about right here. Okay, so that's the second point. Pi over 2 is 1. That's a nice clean number to look at. 3 pi over 4 is halfway between pi over 2 and pi. And that's again about 0.7. And at pi, sine is 0. So already we can see a nice curve forming. Now, once I get past pi, I'm in the third quadrant. So sine is negative, but kind of does the same thing. So right here is 5 pi over 4, and that's about negative 0.7. So about right here. At 3 pi over 2, sine is exactly negative 1. And then it starts to go back up, and we make our way back to 2 pi. And so what I have is is just part of the sine wave. Notice it makes a wave. I say part because it keeps going on and on. So first let me kind of draw a continuous curve to kind of show this pattern. Right, the wave is pretty obvious at this point. But that's it, it keeps going. And so I'm just going to draw an arrowhead here. What happens over here? Well, keep in mind, and maybe I'll kind of highlight these, like this, all of these lines I'm highlighting in green are the different quadrants. Right here is quadrant 1. This is quadrant 2. Notice sine is positive in both those quadrants. This is quadrant 3. This is quadrant 4. And again, if it seems strange I'm saying these are quadrants, well, again, notice this chunk right here is between pi over 2 and pi. In radians, that is the second quadrant, angles between pi over 2 and pi. But angles can also be negative. And so I can realize the exact same thing must happen if I go backwards. And these are my quadrant boundaries if I go backwards. For example, this right here, between negative pi over 2 and 0, that is again quadrant 4. And this is quadrant 3, and this is quadrant 2, and this is quadrant 1. Which means really I can just kind of copy this shape going backwards. And I'll see, I get the exact same thing going on and on and on. And so I'll just roughly plot these points. But again, once we realize an angle in standard position can be negative, it can be positive, it can be any number, then we realize this pattern must just continue on and on and on forever. And we have a really nicely accurate drawn sketch of the sine function. And so cosine, we'll see behaves in the same way. It just starts at a different point, which is quite handy because this wave I have here, cosine is going to look very similar. It just starts at a different point. And so using my table, the cosine of 0 is 1. The cosine of pi over 4 is again 1 over root 2, so about 0.7. pi over 2, the cosine is 0. And now cosine is negative. And so if I just keep filling these out, let's kind of do this for a second. 1. I've gone in one full cycle. I've done the same thing I did with cosine very quickly again. But these are the same values, but for cosine it's a bit different. Again, cosine starts at 1. And so when I plot these points, and again, these are what I'm highlighting in green are the borders between my quadrants. And so they correlate with what I have right here. And so the cosine of 0 is 1, so about right here. The cosine of pi over 4 is about 0.7, so about right here. The cosine of pi over 2 is exactly 0. Going into the second quadrant, cosine is negative. So here we get about negative 0.7 and negative pi. And then it starts to go back up. And if I just plot these points, I can see I have the same sort of shape as before. Now I will say, if you look at this and it doesn't immediately jump out to you as being the same shape as sine, it should get a lot more obvious if I continue this into the negative angles. If you just continue this over here, just continue the pattern. I mean, a wave is a pretty nice pattern, so the next point must be about here and here. And now it becomes quite clear that this is congruent to the sine wave, but not exactly the same as the sine wave. Right. Now it becomes really clear that these waves are the exact same shape. They just start at a different point. If you think of 0 being the start, which is a pretty common place to start, then sine starts at 0, cosine starts at 1. A fundamental thing we don't want to forget. There we go. Sine and cosine functions, nicely graphed right there. Okay, and notice how similar they are. They're waves that go on and forever in this pattern. And of course they go on forever because the input is an angle, and there you can put any number into an angle. They can rotate as many times forwards or backwards as you want. All right, so let's summarize some of these things as well as think about some basic transformations. So in general, if we look at sine or cosine, the domain of both is all real numbers. The range of both is just from -1 to 1, and we saw that a lot actually by the end of the last chapter, that it doesn't matter what value you put into sine or cosine, you'll never get a number more than 1 out or a number less than -1 out. So we see that with the wave. Now, 2 new phrases perhaps are period and amplitude. You may have heard these before if working in physics, but period is a measure of how long a wave is until it repeats. And these both have the same period. Let's look at sine, for example. I'm going to highlight 1 full period. This is 1 full period. Or, I could say this is 1 full period. Or I don't have to start, any particular spot. I could say this is 1 full period, right? That is 1 full cycle. All of these have had the same horizontal distance. Period is a measure of the horizontal distance of 1 full cycle. So what is the period of both of these? Well, let's go back to the first one I started. If I started 0, I got to go all the way to here until I complete the cycle, and now I'm back at 0 and going up. Well, I went horizontally. I went from 0 to 2 pi. So the period from here to here is 2 pi. Or we can also call it the wavelength. And so the period or wavelength, I'll write down as well, is 2 pi. And the amplitude is a measure of the vertical distance from the middle of the wave to the top, or the middle of the wave to the bottom. And so, for example, the middle is, in this case, the x-axis. So it's the distance from there to there, or the distance from there to there. It's the same. A distance is always positive, and that distance is 1. And sine and cosine have the same domain, same range, same period, same wavelength, same amplitude. They're so similar. The only difference between them is they start in different places. So now think about if we had some basic transformations, how would that affect these things? Okay, what if I took sine and cosine and multiply them by some value a? Or what if I multiply the input by some value b? Now, if I were to put brackets here, I could put brackets around this. I don't have to, but if that makes it more clear that that b is times the input of sine, then we probably should put brackets around it. So will either of these affect the domain? No. The domain is always going to be all real numbers. It doesn't matter if you stretch it, flip it, rotate it, squish it. The domain is always all real numbers. The range will change. For example, if I put a 2 right here, then my wave is stretched 2 times higher and 2 times lower. In that case, the range would be from -2 to 2. Let's say I put a 7 right here. Then the wave would go 7 times higher and 7 times lower. It'd be -7 to 7. And so in general, I can say if I just multiply by a, the range is from -a is less than or equal to y is less than or equal to a, with one little extra thing I should say. What if a is a negative number? Well, the range, effectively, it doesn't matter if my a is negative. The range will still go from a negative number to a positive, and so I can take that into account if I put absolute value brackets around this. And again, if I go back, if I look at the graph of -2 sine of x, think about that. Compared to the sine of x, it'll be reflected vertically and stretched by a scale factor of 2, but the range will still be from -2 to +2. And if we don't put the absolute value brackets around it, this would become a +2, this could become a -2. That's it. What about period? How will the period change? Well, A has no effect on the period, but B does. B is a horizontal compression, and so, or a horizontal expansion. And the bigger, if B is more than 1, it's a compression. If B is less than 1, it's an expansion. And so the period of both of these waves is going to be 2 pi times 1 over b, right? Because b is a horizontal stretch. The scale factor is going to be 1 over b. And so you're going to multiply the period, which is normally 2 pi, not by b, but by 1 over b, which is the same as just saying 2 pi divided by b. However, period is a measurement of distance. It's always positive. So if b is negative, there is a reflection, but it doesn't affect the period, so I really should have absolute value brackets around these. Period, like amplitude, is always positive. And amplitude is also affected by these transformations, and it's really whatever a is. The more a is, the more the amplitude's been changed. But again, amplitude is always positive, so I need to put absolute value brackets around it. And we'll look at these in a moment. Lastly, amplitude. Right now, amplitude is pretty easy to figure out by looking at the equation or by looking at a graph. However, later on, this simple formula will be helpful. You can always figure out the amplitude of any wave by taking the maximum value of the output, minusing the minimum value of the output, and dividing that all by 2. That'll always work. Although honestly, this is not very useful right now. It will become useful in later lessons. But it's true, so why not state it? Okay, so let's try to show our understanding of these by sketching some basic transformations. So I want to sketch -2 cos of x. So the first thing I would do is sketch just cosine of x. And remember that cosine starts at 1, and I'm going to focus on just multiples of pi over 2. So what I have here is my quick sketch of cosine of x. Now, I was able to do this quite quickly because I've worked with this a lot. I'm hoping that pretty soon you can sketch cosine as quickly as I did. Notice I'm just focusing on some key points, the high points, where it crosses the x-axis, but this is cosine of x. So hopefully quite quickly we can internalize this and sketch this just as quickly as I sketched it for you right here. So now what transformations do we see here? We see a vertical reflection and a vertical expansion by a scale factor of 2. Back to transformations again. It doesn't matter what order I perform these transformations. I'll do the reflection first and then stretch it. So this point here, if I vertically reflect it, it's now down here. I stretch it by a scale factor 2, it's now right here. So I'll erase my other markings. Do the same thing for this point here. Reflect it vertically, nothing changes. Stretch it vertically, nothing changes, so it's still there. Let's look at this point here. Reflect it vertically, it's now right here. Stretch it by scale factor 2, it's now up 2 times higher. And I can already start to see how this wave is going to behave. The next point is going to be invariant because the y value is 0. The next point is going to be down here, and I can see what my wave looks like. And in general, if I'm going to sketch out a periodic function like this, that means a function that repeats over some period, always try to show one full period. That's it. It's also pretty easy for me to show that point right there. So maybe I'll do that. There we go. There's my graph of y equals -2 cosine of x. All right, let's try this. The sine of negative x. So first, let's visualize the sine of x. Sine starts at 0, goes up to 1, back down to 0, down to -1, back up to 0, and here's my sketch of sine. And I can also go this way. Okay, there's sine of x. Only difference is I'm multiplying the input by a negative, which makes it a horizontal reflection. That's it. So I want to take all these points and horizontally reflect them, which means it'll still start at 0, 0. But now this point right here will be right here. Okay. After that, though, I have a bit of a problem because these are going more and more off my graph. So I got to kind of think beyond literally just reflecting points. However, I do know my wave kind of repeats like, oh, that was pretty lousy. I do know my wave just kind of repeats in the same manner over and over again like this. So hopefully I can see, without literally having to reflect all these points, that the next point must be right here. Ooh, what's happening with my image? There we go. And then it is just a reflection, so the wave will be congruent to what we have. So I can just kind of complete this pattern, and I have something like this. In the end, I didn't really have to reflect many points, literally. I could just kind of visualize the wave. Because a wave is a pretty simple shape. It's not hard to draw a wave. You want to know the details of these. And so I reflect it. You can see these two graphs are horizontal reflections and actually vertical reflections of each other. But this is the graph of sine of negative x. However, it wouldn't be wrong to say that we can now notice that this is equivalent to this. And that will always be true. But for the time being, we don't really need that. All right. So one more before our final problem. There's two transformations taking place here. They're both based on sine. And so let's start again by sketching out sine. Notice for all my sketches on sine, I'm really focusing on just where it crosses the x-axis and where it has a peak or a valley, or trough, it's actually called. All right, so there's sine again. So what's happening here in terms of a transformation? Well, the 2 is a vertical expansion by a scale factor of 2. The x is being divided by 2. That represents a horizontal expansion by a scale factor of 2. Now I will say, if that's not so obvious, if I rewrote the equation like this, y equals 2 times the sine of 1/2 x, that probably gets that perhaps gets more obvious. Right? These two equations are equivalent to one another. Remember again, the scale factor is always the reciprocal of your coefficient of x, of what is being multiplied to x. With that said, I can do these in either order. I'll do the reflection first, vertical reflection. I'll draw that in red. So I'll have points like this. And now I want to horizontally expand this by a scale factor of 2. And I'll draw this in green. So looking at my graph in red, I want to take all my x coordinates and double them. And so I'll start with 0, 0. That's a nice number. And now this here, I'm going to double it. So instead of being at pi over 2, it's going to be at pi. Oh, wait a minute. What am I doing here? What am I doing here? There's no vertical reflection. Oh, you're probably just laughing at me. Fair enough. What am I doing? Anyhow, take 2. So first, the vertical expansion by a scale factor of 2, which I didn't do, should look like this. There we go. Okay, there we go. That is the graph of just the vertical expansion. Now I want to expand this horizontally. So I want to take those points in red and double all the x coordinates. Again, it still goes through 0, 0, but now this point, instead of being at pi over 2, is going to be at pi. This point, instead of being at pi, is going to be at 2 pi. And really, I can start to see what's happening here. And once I have that, I can just kind of continue it down here. It's going to look something like this. I can't even show the full cycle on my grid that I have. But there we go. There's my graph of y equals, as best I can make it, of 2 sine of x over 2. Now, I will say before we go to the final problem that as we start to encounter more transformations, the way I'm approaching this, which is first thinking about the base function, the root function we call it, like sine in this case, and then transforming it, starts to get pretty difficult as I start to add more transformations. But right now, what I've done is a pretty good start. All right, so the last question has two parts to it. I give you a graph, and you want to write a possible equation in the form y equals a times sine bx or y equals a times cos bx. So really, just a vertical stretch of some sort or a horizontal stretch or reflection of some sort, no translations. So let's look at this. If I'm using sine or cosine, and I'm not going to have any translations, I know I have to use cosine for this. And that's because this function starts above the x-axis. And cosine starts at 1, whereas sine starts at 0. And again, that's a fundamental idea we cannot forget. I'll go back to the start of this. You can see it right here. You know, when x at 0, we can clearly see that sine starts at 0, cosine starts at 1. And so if we're not using translations, I have to base this first final problem question on cosine. And so this is going to be some transform version of cosine. What else do I notice? Well, this point here is at a half, which means the amplitude is 1/2, which means I know my vertical stretch must be 1/2. However, I also need to pay attention to the period. Notice here is 1 full cycle. That's 1 full cycle of this wave, which is only pi. So my period is pi, not 2 pi, which is what the period normally is. So now I can see, okay, if the period is pi, therefore there must be a horizontal compression by a scale factor of 1/2. That's the only way to make a period of 2 pi normally go down to 1 pi. You have to have a horizontal compression. And so now I can put this all together in my equation. I can say y equals 1/2 times the cosine of 2x. Keep in mind my horizontal compression by a scale factor of 1/2, I can see right there, and my amplitude of 1/2, I can see right there. It's not possible to write this wave with a sine function unless we apply some sort of translation. We slide it up or something like that, or horizontally translate it, but we're not looking at that yet. Here's the last one. All right, how can I create this wave with just sine or cosine and just a few stretches or reflections? First of all, I see this starts at 0, 0, so I want to use sine. So I'm going to base this on the sine of x. Okay, like before, let's start with amplitude. What's the amplitude of this wave? The amplitude is 4. I can see it goes 4 up or 4 down from the center line. So my amplitude is 4. That's an important thing to write down. So amplitude is 4. Let's look at the period. The period is the length of 1 full cycle. Well, here to here is just half the cycle. In fact, I can't actually highlight a full cycle on the graph we have, but half is pretty useful. From here to here is half 1 full cycle. It's half the wavelength. And what is that? How far is that? It's hard to tell exactly. This is, if I look right here and here, we can figure it out. For example, this is 3 pi over 2, but I don't have to be locked into that part I've highlighted. So there's nothing wrong with what I did. What you may find easier is to look at this half cycle. This I think is easier to deal with. That what I've highlighted in yellow is still half the cycle, right? It's the whole bottom part, and I can visualize how the full thing would look something like that. But if I can figure out what half it is, then I can just double it. And so the length from there to there is 3 pi. Therefore, the period is double of that. The period is 6 pi, right? That 3 pi is the length of half the period. And so if the period is 6 pi, that is 3 times more than normal, which means I know there is a horizontal expansion by a scale factor of 3. And that all hinges on me knowing that sine and cosine normally have a period of 2 pi. This is 3 times more. And like before, I can now take that, and I can take this, and I can put into my equation, but there's still one last thing I'm missing. So let me write that down, though. So I have a 4 here. If the scale factor is 3, it's going to be 1/3 right here. And the last thing I want to do is realize I'm missing only one thing at this point. And what am I missing? Look, if you notice my wave, it starts at 0, but it's going down. That's not how sine behaves. If you look back up here, way up here, sine starts at 0 and goes up. The wave I gave you is going down. And so once we notice that, it's very easy to take care of, but it's also very easy to miss. And so, to be honest, all I got to do is take this and reflect the wave I've written the equation out vertically. And now it's correct, putting a negative in the front. And that equation there will create the wave I've given you. All right, so in terms of things to really focus on, it starts with this. It starts with, you want to be able to draw out the key points of a sine or a cosine wave really, really quickly. You want to internalize it, especially where sine and cosine are 1 and -1 and 0. And I've been kind of talking about that for the last few lessons of chapter 4. And as well then, you want to just immediately know that sine and cosine have a period of 2 pi. You want to know they have an amplitude of 1. And you want to just kind of know those things, and then so you can easily apply a transformation to it. All right, so again, we're going to deal with these sort of things a lot for the next little while, but I'm done for this lesson.